Hello, PyData Global. My name is Aileen Nielsen, and I am presenting today on open source fairness. Just a little bit of background about me. I am a US trained lawyer, but I have also worked as a data scientist at a variety of startups in several different fields. And I now do empirical and experimental research on non-technology, including a lot of empirical work and experimental work thinking about how humans and AI products will interact and what that means when we think about legal concepts, broadly like fairness, but more concretely like redistribution, anti-discrimination, administrative law, and these sorts of things. And I will also make a shameless plug, which is that I have a book called Practical Fairness coming out from O'Reilly in December. I wrote this book for the same reason I'm making this presentation, which is that I think we need far more fairness tools than we have, and we need to make sure that ordinary data scientists and machine learning engineers know about these tools and get them into their just normal toolkit, because this is very much something that needs to be happening all of the time, but is not yet. Here's an outline of this very brief talk. I will first just try to convince you that this is something that we need to be worried about. I can imagine that at this point, many people are thinking, okay, like AI fairness has been a thing like at least for 5 years, especially for the last 3 years. It is such a hot topic. Probably the problems are solved now. So firstly, I want to say, no, they're not, and convince you of that and convince you that you should care. Secondly, I want to think about defining fairness, right? People talk about fairness in machine learning, AI bias, unfair impacts all the time, but I just want to get into that a little bit more. It's a really complicated topic, so I'm not going to give you just a definition of fairness that will solve all your problems, but I want to give you an overview of why defining fairness is even a challenge and what that means for practical work. Thirdly, I'm going to talk about specific fairness interventions. Okay, so I've hopefully convinced you this is a problem, talked about how we can measure the problem, and now we're going to talk about how we can intervene to make better products, to make the world a better place, because the products we are releasing are more fair than they would be without these interventions. And finally, true to the name of the talk, I want to give you an overview of a few open source packages that are out there that have Python interfaces that you can use, because it's easy to sort of think broadly, what is AI fairness? How do I get started? But it's another thing to be able to say, oh, okay, now I can go download this package, play with it, and potentially put it into production, even in my workplace or in my personal projects or in my research. And so I hope you are able to do that at the end of this talk. So new systems, same old problems. We have all heard so much about fairness in AI. Everybody cares about it. Presumably, everybody thinks this is a good thing, provided that their particular definition of fairness could be implemented. But in fact, there are still so many embarrassing facts. So I often think about this when people say, why do we need all this PCness and all this affirmative action? And I'm not looking to get into debates about that, but I will have the same response there of, have you looked at the world? Have you looked at the way the world seems to work? So as much as you think you've heard too much about AI fairness, there continue to be problems with AI fairness, really major problems. So for example, on the left, I have a clip where the housing department was investigating Facebook for a housing discrimination charge. So it was alleged that Facebook was violating housing rights, fair housing rights laws that had been on the books for 40 or 50 years. So these are not new laws, they're old laws. These old laws say that you cannot discriminate on the basis of race or any other protected category when you are offering housing. But in fact, for about a decade, Facebook was enabling just this behavior, because what Facebook allowed people to do is to target ads, including ads for housing, to people according to ethnic affinity, age, religion, gender, all sorts of categories that should be protected for the purposes of housing discrimination. And I should note, none of this was proven in a court of law, so I should really be saying that all of these facts are alleged. But of course, many of them are also just observable even to ordinary people. So it was quite observable that the Facebook advertising platform gave you the ability to advertise in a way that targeted people based on protected categories, such as ethnicity, such as family status, and so on. And that just clearly breaks federal law on fair housing allocation. More recently, the Apple Card was investigated and publicly accused of gender discrimination after a computer programmer, a fairly famous one, noticed that he and his wife were treated quite differently when they applied for Apple Cards, right? So presumably their financials were quite similar, but he noticed that his wife got a much worse offer than he did. And again, we can think, wow, these are sophisticated parties. This was Apple partnering with Goldman Sachs. They surely care about this, right? Because the Fair Credit Act is another act in the US that requires fair access to credit, such as credit cards, such as banking services, and says you cannot discriminate on the basis of gender. And yet that appeared to be what the algorithm was doing. Again, we can't know for sure what the ultimate finding of fact would be in a court of law, but what we can say is it appeared, at least from the media coverage, like that might be a possibility. So even though we've heard so much about fairness, still a problem. Why is that? Well, there are many reasons for this. One is the danger of proxies. So as recently as last October, just a year ago, there was a big study in Science. And what these authors found, Obermeyer et al., was that a very large health insurance company in the United States had unintentionally built a racist decision-making algorithm. The goal of the company had been to identify those people among their insured pool who were most at risk of getting sick, with the thought of, oh, if we can identify them for additional interventions, we might help them get less sick, which is good. They'll get less sick and we will spend less money. And so everybody wins. The problem was that they used as a proxy for seriousness of illness, healthcare spending. But unfortunately, in the United States, it has historically been the case and continues to be that in general, more money is spent on a white patient than on a Black patient, all else equal. And so when even this large, sophisticated company decided to use the proxy of money spent as an indicator of health, it unintentionally replicated the disparity in spending because of the use of the proxy. And so this just shows that even well-intentioned actors who seemingly should have the right economic incentive, they were trying to identify anyone of any race who was likely to get sick, can unintentionally build some very racist products. Why is this? There are other reasons too. Incompleteness of data sets, right? This is one of the reasons people use proxies. Why do they use proxies for seriousness of health condition? Because it isn't necessarily that easy from the mess that we have from electronic healthcare records to determine who is really seriously ill and who isn't. So perhaps to them, on first impression, it seemed like, oh, perhaps money spent could be a very good objective metric for how sick someone is. But in fact, what that was an incomplete data set. There simply wasn't perhaps enough data to identify who was really sick. There are also other forms of incomplete data sets, and sometimes the incompleteness of the data set is itself a problem. So for example, we only record successes in our data sets where we have provided the opportunity to succeed. So if we're thinking again about a financial example like the Apple Card, perhaps when Apple or Goldman Sachs was trying to model who was a good risk and who wasn't, they were using existing data sets, but those data sets were built based on existing decisions. So for example, imagine that if you successfully repay a loan, and that's considered the success, you are marked as a 1, where 1 is the positive and 0 is the negative label. Individuals can't repay loans if they aren't given loans, right? So for the people for whom you are not granting the opportunity, you systematically do not have those people in your data set to find out if you were even correct to deny them the opportunity, right? That is a systematic incompleteness of your data set. Because you're not doing a randomized controlled study. Rather, you're making decisions and then potentially learning from your own decisions. But in the long term, that is just going to reinforce certain systematic unfairness if there is unfairness in the underlying system. So another similar case is individuals can't graduate from a university if they aren't admitted to the university, right? So sometimes when we're making assumptions or building models about who is likely to succeed, we need to think about whether we have even observed the counterfactual, because if we haven't, we're not really giving our model the full space of possibilities as we assume we are. Relatedly, but a different problem, is that sometimes a label means different things for different groups. So in addition to just not giving certain groups access to certain possibilities so that we can observe those counterfactuals, we can also have the possibility that we have a data set with different kinds of people, and those people are actually treated differently, or the process for labeling them is a little bit different, even though that's not apparent from the data set. So perhaps police officers selectively cut people a break with unintentional racial patterns. I'm a police officer. I think I give everyone a fair shake, but perhaps I have some kind of implicit bias so that I'm more likely to be lenient with someone of my own race than of other people, in which case my labeling of people as either criminal or not will itself have some kind of systematic bias. Dangers of labels are even greater than that. So I just talked about how a label can mean different things. Labeling itself also is a problem. To quote Judge Easterbrook, a very famous US judge, depictions of subordination tend to perpetuate subordination, right? So even if labels are correct, and who says they're correct anyway, the labeling can have damaging effects. So for example, I performed this Google search in April 2020, unprofessional hairstyles for work. What's really interesting here is that all of the hairstyles, or almost all of them, are for women. So this already seems to imply that only women commit this egregious breach of having unprofessional hairstyles for work. And what you will also probably notice is there are quite a few Black women relative to white women in these pictures, right? Whereas if I had Googled something else, I might not quite see the same racial balance. In fact, this has been written in the past. At one point, it was only Black women or Black people appearing in these Google search results. So you can say it's gotten more fair in that the label now seems to recognize that many races can be guilty of inappropriate hair, but we don't seem to have fixed the gender problem, that at least right now, if I'm a child learning about the world by searching Google, or if I'm even just an impressionable adult, as we all are, whether we recognize it or not, Google is teaching me that only women can have unprofessional hairstyles. So putting in this label itself is harmful. And sometimes you want to question the label and say, why do we even have an unprofessional hairstyle label? It's one thing to say you have an unsafe hairstyle. Perhaps you work at a construction site and something like a ponytail might not be safe. But why unprofessional? Is that just a label that is itself used as a form of subordination? And like I said, these results are fairly shocking. It gets even worse. Even when I added men to the start of the search, they still return a lot of images about women. So again, I'm getting a very strong message here that it's women who are the problem with the unprofessional hairstyles. More problems with labels. Some of these are related to how humans behave. So in speech, humans often prioritize labeling unusual or non-standard elements of a photo. So if I see a male surgeon, I might just say there's a surgeon. But if I see a female surgeon, I'm going to say, oh, there's a female surgeon. I'm sort of highlighting what I view to be statistically unusual. So what that means is that our labels, again, are systematically different for different groups because of cultural or cognitive reasons, rather than for reasons that are truly related to information. There's an essentializing tendency of machine learning, a bit like there's an essentializing tendency even of how we describe the world. So I just said I would, often people, if they see a male surgeon, will say surgeon, and for female surgeon, female surgeon. This is already some kind of essentialization that even humans do, right? If we see that most surgeons are men, then we're sort of like, oh, surgeon, it's just sort of a man. And otherwise, that's not the norm. Machine learning models do the exact same thing. They sort of essentialize things. So if you take a slightly biased data set, train it with a logistic regression or many other models, you'll often get an even more biased data set. So it's not just that machine learning models replicate bias, they tend to exacerbate it. So for example, in this graphic I have taken from the Washington Post, researchers looked at the disparity between actual share of men versus women in the labor force versus what appeared from the Google image search. And so, for example, what they found was Google image search seemed to heighten the disparity between representativeness of men and women. That is, whatever the disparity might be in the underlying profession, Google image search and whatever machine learning algorithm is powering it heightened that disparity. So as we have a world that's increasingly shaping our inputs via some kind of machine learning algorithm, we are already taking our own essentializing tendencies, and now we are going to have those amplified by machine learning tendencies that do the exact same thing. Another problem, we have this focus on KPIs, right? We tend to be obsessed with accuracy and think that we can't sacrifice accuracy for anything. Here's some good news, though. One of the reasons you should be open to fairness interventions, it turns out that you can often reduce measures of unfairness without sacrificing much accuracy. So this is actually from some findings in 2011, almost 10 years ago. And already they were finding that you could, for example, minimally impact accuracy while substantially impacting a measure of discrimination. And it has only gotten better since then. So you should also be aware that in addition to fairness being a real and pervasive problem, even in 2020, many interventions that you can do that are quite effective will have minimal cost to your bottom line. You also want to be aware that high dimensional data sets are going to have dangerous correlations. So another problem with machine learning is we sort of celebrate unidentified patterns. We need to be aware that some unidentified patterns are actually incredibly problematic. And the classic case of this is anything to do with zip code or geographic area that tends to be highly correlated with race. So, for example, the practice of redlining, in which in the past banks would say, oh, we're just not going to lend to that zip code, that was in fact often a way to be a proxy for race. And so when banks were saying we're not lending to that zip code, what they meant really was we're not lending to Black communities. And so you want to make sure your algorithm is not doing something like that. Blindness does not produce fairness. So just like having a very wide data set is not going to protect you, getting rid of problematic attributes is not going to protect you, because it's possible that even unintentionally, you are treating people differently through your machine learning algorithm, even if you are not explicitly measuring their race or their religion or their gender or any other protected attribute. Finally, by definition, minorities are less attended to by machine learning algorithms. So whenever you use a machine learning algorithm out of the box without some way of acknowledging this, you know by definition that minority groups will likely have higher error rates of some kind, unless they just happen to be very much like whatever the majority group is. This is by definition. You have less training data, so your loss function is going to weigh those losses less. Okay, and here's just a graphic example of this that I have borrowed with permission from Professor Aaron Roth. So you can see how this group, which is the numerical minority, is not going to be well served by a model trained on the majority. And that's quite unfortunate. Okay, on to our next topic, defining fairness. Really difficult to do, as it turns out. There are sort of major classes of fairness definitions. One is demographic parity, that basically says we think all groups that are sort of meaningful groups to define, such as gender or race or what have you, we think those metrics should produce equal outcomes. You know, Blacks and whites should have equal outcomes. Men and women should have equal outcomes. That doesn't mean every individual, but it means approximately the same success or failure rates. Counterfactual fairness. This is where we say, well, since we think something like race shouldn't matter, the way we'll assess fairness is to change the race or the gender or what have you while holding all else equal. And the less the output changes, the more fair, the fairer the system is. This is okay definition-wise. It can be difficult to test in practice. And so finally, we have this thing called equality of odds. This is a bit like demographic parity, but instead of saying that the success rates for all groups should be the same, the authors narrow in and say, no, it's more that the probability of the false positive and true positive rates for individuals who have a true positive rating should be equal. So of the individuals who deserve the opportunity, of that subset of the population, the proportion of individuals getting the opportunity should be the same. And that's why it's called equality of odds, or sometimes when it's more narrowly defined, equality of opportunity. This is a little bit different from demographic parity because it enforces the parity only at the level of a subgroup, the successful individuals. That is, the individuals who should be successful. We look at their rates rather than the whole population rate. These are just some classes of definitions. There are literally dozens of definitions of fairness. There are fairness inconsistencies, though. Different group-oriented definitions of fairness can be inconsistent in the sense that you can't equalize them at the same time. So in many systems, you can't have the same false positive and false negative rates, say for different racial groups or gender groups at the same time. If you equalize the false positive rate, then the false negative rate won't be the same. If you equalize the false negative rate, then the false positive rate won't be the same. Likewise, group-oriented definitions of fairness can come into conflict with individual levels of fairness. So you might say, well, I want the success rates for men and women to be about the same, but also say to enhance individual fairness that when I look at an applicant and the only thing I change is male versus female, that those should be very consistent results. It turns out, again, mathematically, it's hard to get all of that at the same time, to have those group-wide fairness metrics and the individual fairness metrics looks the same. I won't go into this. There is a number of publications as to why this is. I recommend Kulikova's paper on this in 2016, merely because it is very accessible. You can work through with simple algebra, and you can see that it's necessarily true that there are some tensions, that if you have fairness definition A fulfilled, you might not be able to have fairness definition B fulfilled. For example, you can't have the same number of false positives and false negatives per racial group when you're thinking about criminal recidivism modeling. And it turns out that the reason for that is that if the underlying base rates for different populations are different, then you cannot match their error rates. That is simply a mathematical certainty for these sorts of models. So this is more of that math. I would encourage you to look at it in the paper. Also, so that's sort of one complication with fairness metrics, is there are so many ways to define fairness and they contradict one another. And so far, actually, when I've been saying fairness, what I have really meant is anti-discrimination, right? Is thinking about the fact that we don't want people treated differently simply because they belong to some category. But there are other values implicit in fairness that I'm not addressing today, but you want to think about. Values like consent, as far as those relate to data privacy issues. Values like the material rewards for production and distribution of information. So people talk about data labor. Why is it that all of the value produced from the big data economy is just going to digital entities? What about the people like you and me who are observed? And our data has some value, and why don't we receive that? So you can think about this sort of distribution element of fairness. Privacy and security, right? There are all sorts of security problems and privacy problems with machine learning models right now. This is tremendously difficult and complicated to get right, but unfortunately, most data scientists don't even try. That is, we know that there are adversarial attacks, that there are privacy attacks, that sometimes if you're clever, you can extract training data from the model itself, right? So we know that perhaps the data itself is under attack through the models. That's also about fairness, because if people have provided their data with consent for a model to be trained, that doesn't mean they have provided consent to face these other privacy and security issues. There's also autonomy. Often we're using machine learning to undermine autonomy. We're trying to build distracting products, addictive products, products with so-called dark patterns where we exploit cognitive biases to defeat what people want. We say, oh, you wanted to buy X. How about buy X and Y? And we have sort of clever models to predict when people will be vulnerable. That doesn't sound very fair either. So those are other fairness considerations that don't get talked about enough, but that you should be thinking about too. So I'm focusing in on anti-discrimination, but there are other fairness elements, and they have other metrics. Okay, so now we talk about fairness interventions. So hopefully I've convinced you that the specific fairness problem of anti-discrimination is a problem. I have recognized that there are many ways to define anti-discrimination, but I've also explained to you that sometimes those definitions are in tension, because many definitions can seem compelling, but I can't satisfy them at the same time. I can't make everything perfect at the same time. Now I want to talk about, well, you want to do something about fairness. How and where do you do that? Here's sort of Wolfram's version of the data science pipeline. And I want to think about how we intervene around here. And my point to you is that at every point along this stage, there are fairness questions we can be asking, from the very formulation of the question, to how we clean and explore the data, to how we build the model and validate it, to how we decide to deploy that model. So fairness interventions by pipeline stage. If you think about the purpose, why are you even building a model? Are you building a model to target a vulnerable population, or are you building a model to empower a vulnerable population? That's already a fairness issue. Thinking about the data you select, are you sure with the data you're selecting that you're selecting it for the right reason, that you're sure it has good quality, that you can check whether there were systematic biases? Remember all the problems I highlighted at the beginning of the talk. They almost all fall into data selection. How are you choosing a proxy? If you're choosing a proxy, how do you know that proxy won't introduce additional bias, and so on? Then there are these three phases: pre-processing, in-processing, and post-processing. These refer to ways in which you actually change your data to make it have a less discriminatory outcome according to whatever fairness metric you choose. So it can be a group fairness metric, like I think different groups should have the same error statistics. It can be an individual metric, like I want highly consistent decisions where if all I do is change the race of an individual, I get the same outcome, and that's what I really care about. These sorts of metrics. But you can use them for pre-processing to sort of modify the way you represent your data. You can use them for in-processing, where you train with a loss function that is sensitive to fairness, or post-processing, where once you identify labels, you might change them to enhance the fairness of the outputs. There's also performance monitoring and stress testing after your product is entirely finished, and black box auditing. So some pre-processing examples. Sometimes what you might want to do is do something like randomly flip sensitive attribute labels to remove whatever information might be correlated with those sensitive attributes. You can reweight data points to remove disparate impact. You can say, I am going to make this data set look as though there is no difference in population A versus population B. And the way you might do that is for the underprivileged population, upweight their successful individuals, and for the overly privileged population, downweight their successful individuals, and bring about parity that way. You can also think about ways to represent the space for the input data that will balance the disparate impact fairness metric. So here's some recommended reading in this area. Then there's in-processing. In-processing usually relates to modifying your loss function with some kind of discrimination penalty. So in addition to an incorrectness of label penalty, you can have a discrimination penalty. And that can work with any of those fairness metrics we've talked about. You can also use adversarial learning patterns where an adversary tries to learn the membership of, for example, a sensitive attribute like race, while the model tries to learn an outcome. And so you try to build a model that both gets the outcome right, but also provides as little information as possible about the sensitive attribute. And so here are two papers I'd recommend that develop methodologies to do that. And then post-processing. Post-processing is when you take a score and you know that the system producing the score is still resulting in some kind of discrimination, depending on what metric you are using for discrimination. And then you either randomize the labels, perhaps the labels close to the decision boundary, and you say, well, discrimination is probably happening close to the discrimination boundary. So right around here, I'm going to randomize the labels, perhaps of the underprivileged group or the overprivileged group or both, to try to introduce a little more noise and a little less discrimination into the outputs of my model. You can also do this in a way where you equalize along some cost function. So if you recognize that certain kinds of mistakes are more or less costly, that is another way you can deal with this. So that's post-processing. And then, of course, you have auditing. In this case, you choose a fairness metric and compute these as appropriate, or you measure and report the influence of input variables. These are two tactics people take for auditing. Okay, so now that we've done a whirlwind of fairness interventions, concrete ways that you can take action to make your products safer and fairer and more reflective of the world as you would like it to be, how do you build these? Well, here's some open source software. All of these packages are quite easy to use and well documented. So I'm just going to give you an overview. AIF 360 is a project from IBM. They offer pre-processing, in-processing, and post-processing options, which are quite handily broken down here. They also have commonly used data sets. So there are certain data sets you see in the fairness community a lot, such as the German credit data set, the Compass data set, the adult income data set, which is US adult income. Those are all in there. Quite a large array of fairness metrics are built in. And what's really nice about this data set or code base rather, is that they implement many cutting edge published algorithms. So unfortunately, academics do not always contribute to one standard code base. Often they will just release the code for their paper in their own GitHub repository. So you don't easily have a way of using many state-of-the-art algorithms in just one package. But that is what AIF 360 does, and that's quite nice, both because of the sponsorship of IBM and the fact that it's quite up to date. And just to show you how easy the example code is to use, you can see here's an example of a pre-processing tactic. So you pre-process, you train, and then you can already compute a metric just in a few lines. So the struggle here is knowing what these metrics mean and knowing what these techniques are. You have to have the conceptual basis to use them, but once you do, the code is already written for you. Another example is the IQTAS project. So this is out of the Center for Data Science and Public Policy at UChicago, although I believe they've moved to Carnegie Mellon. But this product, rather than being about fairness interventions, is about fairness auditing. And they give you either a web interface, a command line interface, or a Python library. They have an extensive implementation of fairness metrics. And what they allow you to do are reports like this, where you will get a breakdown of the bias. They'll tell you sort of what performance metrics they used, what bias metrics they considered, what groups they considered as far as sensitive attributes, and you will get visual representations of the bias in your model. So this can be a way to set up a nice automatic check for bias. They also include a Python library. So if you want to do your own coding, you can do that as well. And I show you here just how simple it is. And again, you get these automatic representations. So far I've told you sort of how you can actively intervene in your process with AIF 360, and then IQTAS is one tool where you can automate the auditing. Here's another one, FairML. It's a little bit different. IQTAS tends to look at fairness metrics and how they vary by group. FairML instead looks at feature importance. So they sort of look at the inputs rather than the outputs. So how are these inputs affecting my outputs? And seeing if some of the inputs seem to matter more than they should. So for example, one example they provide, and again, very easy to use interface, is that if you look at, I believe this is the Compass algorithm, a very famous one, they find that African American seems to matter a whole lot, but of course it probably shouldn't, right? So something like this, showing that an input that shouldn't matter is in fact highly influential to the outputs of the model, is another way to look for fairness problems. And notice this addresses both explainability and anti-discrimination. And finally, there's the ML Fairness Gym. This comes out of Google, although it is unofficial, so Google will not necessarily maintain it. But what they introduce is this dynamic rather than static notion of fairness. They say you can't just look how your model is doing now. What you probably want to do is simulate what are the effects of deploying your model? Because once you put your model into effect, it produces an action, which in turn influences the environment. But the environment that your algorithm has acted on now produces an observation, which you might use for learning. And so they recognize that there could be a cycle where the algorithm is both influencing the world, but then influencing itself because it will continue collecting data. And you can think in this way, how might I have these sort of feedback loops where I might have runaway bias or runaway unfairness? Or also, how can I just think dynamically about how my model is going to impact the world? And so what they do is they give you a simulation environment. You think about the sort of fairness metrics you want to use. You think about what kind of agent you want to use, and they have coded up quite a few. So you can think about college admissions or classifiers or allocators, and then they let you play that out over time. And they say, okay, in this case, this is sort of over time what things are going to look like. So maybe over time things get more fair or less fair, or distribution gets better or worse. But this is something that has also been missing from the fairness literature and is quite useful. So that's another take. So just to give you an overview, AIF 360 will give you state-of-the-art cutting-edge ways to modify your training process or your training data to enhance fairness. IQTAS and FairML will help you audit a model, including a black box model. And then the ML Fairness Gym will help you think about the dynamic, temporally sensitive aspects of fairness, thinking about how fairness has to reflect an evolving environment and shouldn't just be a static view of your algorithm. So thank you for your time, and I look forward to meeting you at the Q&A sessions.